You know how sometimes a simple number just isn't quite enough information?
Right.
Like if you tell someone you walked 5 miles, okay, great. But if you say you walked 5 miles northwest, suddenly that direction, it changes everything, doesn't it? It's not just about how much, but also, where or how. So today on the deep dive, we're going to really get into the world of vectors. And these aren't just like abstract math things for textbooks. They are absolutely fundamental in so many fields: physics, engineering, computer graphics,
Yeah.
even understanding complex data.
That's absolutely right. Our mission today, using the great source materials you've pulled together, is to unpack vectors, really figure out what they are, how they work, how we do math with them, and why they're such a critical tool. We're aiming for those, those aha moments that make even complicated ideas feel clear.
Okay, let's dive right in then. What is the fundamental difference between that 5 miles, the simple number, and the 5 miles northwest? Why is that direction part so important mathematically?
Well, it really boils down to the difference between scalars and vectors. A scalar is just a number. It tells you the magnitude, the how much, like 60 miles per hour speed or maybe 20 degrees Celsius temperature, just one value.
Okay.
But the second you add a direction, now you have a vector. So velocity isn't just 60 miles per hour, it's 60 miles per hour north. Or a force isn't just 10 pounds, it's 10 pounds downward. Vectors need both things.
Yeah.
A magnitude, which is their size or length, and a direction.
Right, and what's kind of wild is that, mathematically speaking, the vector's actual starting point, its position, doesn't matter, just its length and the way it's pointing.
Yeah.
That seems counterintuitive almost.
It does seem that way at first, but it's crucial. That idea that position is irrelevant is actually incredibly powerful. It means the same force vector, the same push or pull, can be thought about acting at different places. It just describes the force itself, how strong and which way, not, where exactly it originates.
Huh. Interesting. Okay, let's make this concrete. One source mentioned something surprising, the PostScript language. For drawing graphics, how do vectors show up there? Yeah, imagine drawing a triangle. The commands might look like 0, 0, move 1, 1, line of post stroke.
Yeah.
Each part there, like line to co, it implicitly tells you a direction and a distance, right? Move to 0, 0, then draw a line from there to 11, 1, then maybe from 11, 1 to 1, and then back to 0, 0. So mathematically, we can capture each of those movements with a vector. We use this ordered pair notation, like x, y, where x is how much you move horizontally and y is how much you move vertically. So going from the origin, 0, 0, to the point, that's the vector 11, 1.
Exactly. And going back, say, from 11, 1 back to the origin.
That would be backwards 1 horizontally, backwards 1 vertically. So Mathematic's 1.
Precisely. And those numbers, the x and y and the pointy brackets x, y, those are the components of the vector. They're the specific instructions for movement in each direction.
All right, so we have these instructions, these components. How do we picture them? How do we draw a vector?
Geometrically, we draw it as a directed line segment. Basically an arrow. The arrow's length represents the magnitude, the how much. And the arrowhead shows the direction. Simple as that.
And crucially, like we said before, if two arrows have the exact same length and point in the exact same direction, they represent the same vector. It doesn't matter if one starts here and the other starts way over there. They're equal.
That's a really key concept because the starting point doesn't define the vector. We often find it useful to talk about a vector in standard position.
Standard position. What is that?
That just means we draw the vector with its tail starting at the origin. So 0, 0 in 2D or 0, 0, 0, 0 in 3D. For example, the vector 3, 4 in standard position starts at 0, 0, and its tip, the arrowhead, ends up at the point 3, 4.
Ah, okay.
But remember that same exact vector, 3, 4, could also be drawn starting at, say, the point.
Right.
Where would its tip end up then?
Let's see. Start at 11, 1, move 3 horizontally.
Yeah.
So x goes to 4. Move 4 vertically. Y goes to 5. So it would end at 4, 5.
Exactly. Same vector, 3, 4, because the displacement, the change, is identical. 3 units over, 4 units up. It leads to a simple way to find the vector between 2 points. If you start at point Q equal Q1, Q2, and end at point R, R1, R2, the vector QR is just R1, Q1, R2, Q2. Just think final minus initial for each component.
Got it. And notation-wise, we use those pointy brackets and for the vector components, right? To make it clear, we're not talking about a point, which uses parentheses.
Yeah.
Sometimes you also see a little arrow over the letter representing the vector.
Yes, both are common conventions. You might also hear the term position vector. That's specifically the vector that goes from the origin O to some point P. We'd write it as OP.
Makes sense.
And this isn't just for 2D or 3D space. Vectors can exist in any number of dimensions. We talk about n-dimensional space, or Rn. A vector there just has n components, v1, v2, vdn.
Higher dimensions. Okay, that can feel a bit abstract. Let's use that fun example from the sources, the classroom coordinate system.
Ah, yes, the professor's head is the origin.
Right, so the professor decides their head, which is 5 feet off the ground, is the origin,
Correct.
0. Now, your friend Alice is at point A, 936.2.5. There's a projector at B, 0, 1, and 3, and another friend, Carlos, over at C, 222.05, all in feet. So just visualizing that, the vector OA from the origin to Alice, what does that represent?
Since the origin is O, OA is just the position vector of Alice. So it's 9, -6, -2.5. It tells you how to get from the professor's head to Alice.
Okay. Now, a bit trickier. What about the vector AB, the one from Alice to the projector?
Right, so we use that final minus initial idea. B is the final, A is the initial. So BA component by component, 0, 9, 1, -6, and 3, -2.5.
Okay, so that's nanig is 9, 1 plus 6 is 7, and 3 plus 2.5 is 5.5. So AB equal -9, 7, 5.5.
Exactly. And notice what that vector tells you. It's not where Alice or the projector are, but the actual displacement, the journey between them. That's the power of vectors. They capture change, movement, relationships.
That's a great distinction. Movement and change, not just static location. And speaking of being precise, when are two vectors actually considered equal? If I have U1, U2, and V1, V2.
They are equal if and only if their corresponding components are identical. So U1 must equal V1 and U2 must equal V2. That's it. Same applies in Rn. All n components must match perfectly.
All right, so we know what they are, how to write them.
Mm-hmm.
How do we actually do math with vectors? Can we add them, multiply them?
Yes, absolutely. And vector addition is surprisingly straightforward, where you just add the corresponding component. So if you have U1, U2, and V1, V2, then U plus V is simply U1 plus V1, U2 plus V2. Same idea for any number of dimensions.
And geometrically, what does adding them look like?
Two main ways to picture it. One is the tip-to-tail method. You draw the first vector, U. Then starting from the tip, the arrowhead of U, you draw the second vector, V. The sum, U plus V, is the vector that goes from the tail of U directly to the tip of V. It's like following one displacement, then the next. The other way is the parallelogram law. If you draw U and V starting from the same point, they form two adjacent sides of a parallelogram. Their sum, U plus V, is the diagonal of that parallelogram starting from the same point.
Okay, let's use that lost friend example again. That seems perfect for addition. Remind me, the first vector was U equals 3 equals 4, from the car to the expected meeting spot.
That's right, 3 kilometers east, 4 kilometers north.
And then the ranger gives new directions, V equals 1 below 4 from where you are now. So 1 kilometers west, 4 kilometers north.
Correct.
So the total displacement for the car all the way to the ranger's suggested spot is U plus V. We just add the components, 3 plus mine equals 1 for the east-west part, and 4 plus 4 for the north-south, which gives us 2, 8.
Exactly. 2 kilometers east and 8 kilometers north from your starting point, the car. See how adding the components automatically combines the movements in each direction.
Yeah, that's really neat. Okay, so that's addition. What about multiplication? Can you multiply a vector by just a regular number?
You can. That's called scalar multiplication. You take a scalar, which is just a real number, let's call it k, and multiply it by a vector v. The result is kv, kv1, kv2, kvvn. You just multiply each component by that scalar k.
And what does that do geometrically?
It scales the vector. It changes its magnitude, its length. If k is, say, 2, the new vector 2v points in the same direction as v but is twice as long. If k is bigger than 0.5, it's half as long.
And if k is negative?
If k is negative, it reverses the vector's direction. So Neckel 1v, or just 1v, has the same length as v but points in the exact opposite direction. Nectarcer 2v would be twice as long and point opposite.
Back to the lost friend. The drone spots them, but they're 3 times as far from the car as that first spot P, but in the same direction. So the original vector was U, 4, Duma 4.
Right. So the vector to the friend's actual location would be
3 times that, so 3U,
Yeah.
which is 33, 34, or 9, 12.
precisely. You just scaled the original displacement vector.
Okay. And subtraction. Can we subtract vectors?
We can. We define VU simply as V plus nec of 1U. You just add the negative of the vector you want to subtract.
Makes sense.
Geometrically, if U and V start at the same point, VU is the vector that goes from the tip of U to the tip of V. It's the vector you'd need to add to U to get V.
Gotcha. Now, you mentioned components. There are these special vectors, right? I, J, and K.
Yes, the standard unit vectors. Extremely useful. In 2D, I is 1, 0, 1 unit along the positive x-axis, and j is 0, 1, 1 unit along the positive y-axis.
And in 3D, we add K.
Correct. K equals 0, 0, 1, 1 unit along the positive z-axis. They're called unit vectors because their length, their magnitude, is exactly 1.
And why are they so useful?
Because they form a basis. That means any vector can be written as a combination of them. For example, our vector 304 in 2D We can write that as 3i plus 4j. It explicitly shows the components in the x and y directions. You see this notation a lot in physics and engineering.
So 3i plus 4j is just another way of writing 3car.
Exactly. And a, b, c in 3D is ai plus bj plus sec.
Okay. And do these operations like adding vectors or scalar multiplication follow the usual rules of arithmetic?
They do, largely because they operate component-wise. Vector addition is commutative, u plus v plus u, and associative, u plus v plus w, u plus v plus w. Scalar multiplication distributes over vector addition, ku plus v plus kv. All the familiar properties generally hold.
Now, here's a potential trap you pointed out from the sources. Why can't we calculate something like 2, 2, 4, 7, 3 fad scored 7? It looks like vector math.
But look closely at the vectors themselves. The first one, 2, 4, 7, is in R3. It has 3 components.
Right.
The second one, mash and pi, squared C7, is in R2, only 2 components. You can't add or subtract vectors that live in different dimensional spaces. It just doesn't make sense mathematically, like trying to add feet and seconds directly.
Good warning. Always check the dimensions.
Yeah.
This idea of combining vectors like 3i plus 4j, you mentioned it's called a basis. Is there a term for combinations like AV plus BW more generally?
Yes, that's called a linear combination. It's a fundamental concept. It's basically saying you can create new vectors by scaling and adding existing ones, v and w in this case scaled by a and b. This is how we can often describe entire spaces or planes using just a few key vectors. It hints at much deeper stuff in linear algebra.
And related to scaling, what about parallel vectors? When are two vectors parallel?
Two non-zero vectors, v and w, are parallel if one is just a scalar multiple of the other. So if v, a, b, ok, w for some non-zero scalar k, they lie on the same line through the origin, pointing either the same way if k is positive or in opposite directions if k is negative.
But the zero vector isn't parallel to anything.
Right. The zero vector 0, 0 has zero magnitude and no defined direction, so the concept of parallel doesn't really apply to it.
Okay, so we've covered direction, components, adding, scaling.
Right.
But what about the length itself, the magnitude? How do we calculate that precisely?
Right, the magnitude. We usually write it with double bars, like v, and it comes directly from the Pythagorean theorem or the distance formula. For a vector v equals v1, v2, vbn, its magnitude is velot v12 plus v22 plus this best vn2.
Okay, so for that vector AB equals 2 bubble 4 we had earlier?
Its magnitude AB would be scort 22 plus 42. That's tort 4 plus 16, which is scort T20. That's its length.
Got it. And this ties into those unit vectors you mentioned, like I and j. They have a magnitude of 1. Why are unit vectors so important?
They're incredibly useful because they purely represent direction. They've stripped away the magnitude part, leaving just the which way. This is vital in, say, computer graphics for calculating light reflections, or in physics for defining coordinate axes, or even in machine learning for comparing directions of data vectors.
And how do you find a unit vector if you have just any regular vector?
Simple. If you have a non-zero vector v, you just divide it by its own magnitude. So the unit vector in the direction of v is u equals vv.
So for our AB equals 2 over 4, its magnitude was scored in 20.
Right.
The unit vector would be first scored in 24.
Exactly. That new vector points the same way as 2L4, but has a length of exactly 1.
Okay, so a couple of quick questions based on the activities in the sources. Is u plus v always the same as u plus v? Like, does the magnitude of the sum equal the sum of the magnitudes?
No, not usually. Think about the triangle again.
Yeah.
uv and u plus v form a triangle using the tip-to-tail method. The triangle inequality tells us the length of one side, u plus v, must be less than or equal to the sum of the lengths of the other two, u plus v.
When would they be equal then?
Only if u and v point in the exact same direction, or if one or both of them is the zero vector. Then they just add up along the same line.
Makes sense. And how does the magnitude of TV relate to the magnitude of v if t is just a scalar?
TV is equal to TV. Note the absolute value around t, because magnitude is always non-negative. Even if t is negative, which flips the direction, the length is scaled by the absolute value of t.
Right. Length can't be negative.
Yeah.
Okay, last one. Of the standard vectors I, j, and the vector I plus j, which ones are unit vectors?
Well, I also holon 0. Its magnitude is square t 12 plus 2 equals 1. So I is a unit vector. Same for j, 0, 1, 1. Magnitude is square 2 plus 12 equals 1. But I plus j is the vector along 1. Its magnitude is square plus 12 equals what? T2. So I plus j is not a unit vector.
Got it. Okay, we've built up a solid understanding. Definition, representation, operations, magnitude.
Yeah.
So how does this actually play out in a real world problem? Let's look at that force and tension example.
Yeah, the painting example. It's a classic application. So you have a painting, it weighs 50 pounds, and it's hanging from 2 wires attached to the frame.
Yeah.
One wire, let's say its tension vector is u. goes off to the left and makes a 60-degree angle with the horizontal ceiling or support. The other wire, tension vector V, goes to the right and makes a 45-degree angle with the horizontal.
And the goal is to find the tension in each wire, which means finding the magnitudes, U and V.
Exactly. We need to find out how strong those forces are.
All right, how do we set this up using vectors?
We can treat the point where the wires meet the painting, let's call it O as the origin, 0, 0. The painting's weight is a force vector, W, acting straight down. Since it's 50 pounds downward, and if we say J is the upward unit vector, then W is 0, negative 50.
Okay, weight pulls down.
The tension vectors, U and V, are pulling upwards and outwards along the wires, counteracting the weight. The key concept here is equilibrium.
Meaning everything is balanced.
Precisely. For the painting to hang still, the net force must be 0. This means the upward forces must perfectly cancel the downward force. So the vector sum of the tensions, U plus V, must be equal and opposite to the weight vector W. Mathematically, U plus V equals 0, 50.
So U plus V must equal 0, 50?
Exactly. Now, we don't know the magnitudes U and B yet. That's what we want to find. But we do know their directions, the angles. We can use trigonometry, sines and cosines of those 60 and 45-degree angles, to write the components of U and V in terms of their unknown magnitudes.
Ah, so you'd have an x component for involving U and cosine 20 maybe, and a y component with U and sin 120, and similarly for V with its angle.
You've got it. Then the vector equation U plus V equals 0, 50 becomes two separate scalar equations. One for the x component summing to 0, since the painting isn't moving sideways, and one for the y component summing to 50 to balance the weight.
And that gives you two equations with two unknowns, U and V. You can solve that system.
That's the process. Solving that system gives you the magnitudes, which are the tensions in the wires.
That's a really clear example of how breaking forces into vector components makes a complex situation solvable. It makes you think, doesn't it? What if those wire angles were different, say much flatter, closer to horizontal?
Well, think about the trigonometry. If the angles are flatter, the sine components, the vertical lift, get smaller for the same magnitude. To get the same vertical lift needed to hold the 50 pounds, the overall tension U and V would have to get much larger.
So hanging a picture with wires that are nearly horizontal puts way more tension on them than using steeper angles. You'd need much stronger wires.
Exactly. It's a practical design consideration revealed by the vector analysis.
Wow. Okay, we have definitely covered a lot of ground today in this deep dive on vectors, from just, representing a simple walk northwest to figuring all forces on wires. These arrows are clearly doing some heavy lifting, mathematically speaking.
They really are. Just to quickly recap the big ideas, vectors have both magnitude and direction, unlike scalars. They're independent of position. We can represent them with components x, y, z and visualize them as arrows. We can add them tip to tail or parallelogram and multiply them by scalars, which scales their length or reverses direction. Magnitude v measures their length, calculated using the distance formula. And unit vectors give us pure direction. They're just essential tools for physics, engineering, graphics, data, you name it.
And for you, the listener, getting comfortable with vectors really is like learning a fundamental language. It helps make sense of so much of the physical world and how things change and interact. It's more than just math. It's a way of thinking.
Absolutely. And maybe a final thought to consider. We've talked about vectors representing state, like position or force. But how does calculus apply to vectors? If we think about how vectors change over time, like velocity changing, which is acceleration, how could understanding vector calculus allow us to, say, predict the path of a planet or model fluid flow, just by looking at the rates of change of these directional quantities?
That definitely opens up a whole new dimension. Something to think about. That's all for this deep dive. Until next time, keep exploring.